Now we would like to compare these modes of all these modes of convergence, these 7 modes we have defined until now. But before that, let me give another definition, and this is of the L infinity norm. So suppose that f is a complex valued measurable function on X. So the first definition is an essential supremum or essential bound of f is a number, positive number m, such that mod fx is less than or equal to m for mu almost everywhere x. So this bound holds for almost every x. So this is outside of a null set in X. So any such positive constant m for which this condition is satisfied is called an essential bound of f. Now the essential supremum or L infinity norm is defined to be the infimum of all essential bounds of f. All essential bounds of f, which means that we can denote it as f L infinity like this. So if you want, you can also write the measure mu on it, but we will usually drop this measure mu from the notation and simply write it as L infinity like this. And this is by definition the infimum of all numbers. So I am assuming also that m can be plus infinity. So here also we can take m to be plus infinity. Because your function may not be bounded on may not have any essential bound. In that case, m will be plus infinity. So here it is the infimum of m lying in this extended non-negative reals such that m is an essential bound of f as defined above. So this is the L infinity norm. So one immediate result is the following. So if fn is a sequence of complex measurable functions on X, and f is another complex measurable function, is measurable, then fn converges to f uniformly almost everywhere. So what we call also essentially uniformly, convergence essentially uniformly, if and only if this norm L infinity norm of the difference L infinity goes to 0 as n goes to infinity. So we see that convergence in the L infinity norm is equivalent to convergence uniformly almost everywhere or essentially uniformly. So let's see a quick proof. So we can recall the definition of convergence uniformly almost everywhere. So Fn converges to F uniformly almost everywhere if given epsilon greater than 0 there exists a capital N such that, so I missed something, which is this is for all n greater than or equal to n. This condition holds for mu almost every x. So to show the forward implication, we have that if Fn converges to F uniformly almost everywhere given epsilon greater than 0, there exists a capital N such that for all n greater than or equal to n, we have mod of Fnx minus Fx is less than or equal to epsilon for all x mu almost everywhere. So outside of a mu null set, this relation holds for all n greater than or equal to capital N. Now this means that by definition of the of an essential bound, this means that epsilon is an essential bound for the function Fn minus F mod. So absolute value of Fn minus F. So this is this implies that the L infinity norm of Fn minus F, so you can put a modulus if you like, but it would be the same thing. So it says that it implies that the L infinity norm of Fn minus F is less than or equal to epsilon, because on the right hand side this is an essential upper bound, and on the left hand side this is infimum of all essential upper bounds. So this the difference has L infinity norm bounded above by epsilon, and this is valid for all n greater than or equal to n, and this implies that this L infinity norm of the difference goes to 0 as n goes to infinity. So this is the forward implication, and I leave the reverse implication as an exercise. So prove the reverse implication left as an exercise, which is essentially the same thing as we have seen in the forward implication as an exercise. So we see that uniform convergence almost everywhere is the same as convergence in the L infinity norm. Now we can see some easy implications from that follow from the definitions of these modes of convergence. So the first one is that if Fn converges to F uniformly, then it converges to F in L infinity norm. Remember that this was uniform convergence almost everywhere. It was equivalent to uniform convergence almost everywhere. So this implication is actually trivial. So this is trivial. The second one is Fn converges to F in L infinity norm, implies Fn converges to F almost uniformly. The third one is Fn converges to F almost uniformly, implies Fn converges to F pointwise almost everywhere. Fourth one is Fn converges to F in L1 norm, implies Fn converges to F in measure. And the last one is Fn converges to F almost uniformly, then Fn converges to F in measure. So the first one we have seen is it's trivial. This second, I will only do the second and fourth in this lecture, and I leave the third and fifth for the next lecture. So the second and fourth one are also quite easy. So I will only do second and fourth, and these two will be taken up in the next lecture. So let me do the second and fourth one. So for the second one, we need to show that Fn converges to F in L infinity norm implies Fn converges to F almost uniformly. This was our second statement. So let's write down what it means for convergence in L infinity norm. This means that given epsilon, so this is to show given epsilon greater than 0, there exists a capital N such that for all n greater than or equal to capital N, this L infinity norm of the difference of Fn and F, this is less than or equal to epsilon. And so this is convergence in L infinity norm, and convergence almost uniformly, this says that given epsilon greater than 0, there exists a set E. So this set E depends on epsilon, and it is a measurable set in X such that the measure of E epsilon is less than or equal to epsilon, and Fn restricted to E complement converges to F restricted to E complement uniformly. So we say that Fn converges to F uniformly outside of E. So this is convergence almost uniformly. So if you have convergence in L infinity norm, we have seen that this is the same as, this is equivalent to convergence uniformly almost everywhere. So this means that, so we have given epsilon greater than 0, there exists a capital N such that for all n greater than or equal to capital N, mod of Fn x minus Fx less than or equal to epsilon for x outside a mu null set, let me call it E. This is the same as saying that Fn converges to F uniformly outside E, and of course the measure of E is equal to 0. Measure of E is equal to 0, and of course this is less than or equal to epsilon. Notice that this mu null set E also depends on epsilon. Even though it is a null set, it may change when you vary epsilon. So now this implies that Fn converges to F almost uniformly, because your exceptional set is precisely this E epsilon that we have chosen here, which is a mu null set. So this proves 2. For the fourth part, we have to show that Fn converges to F in L1 norm implies that Fn converges to F in measure. So we have to show that when Fn minus F has L1 norm going to 0 as n goes to infinity, then this implies that the measure of this set mod Fn x minus Fx greater than or equal to epsilon goes to 0 as n goes to infinity. So this proof is quite easy, because these kind of sets we know how to estimate, and this is by the Markov's inequality. So by Markov's inequality, for any positive epsilon, we have that the measure of the set of points in X such that fnx minus fx as modulus greater than or equal to epsilon is bounded above by 1 over epsilon times the L1 norm of fn minus f. So this was the statement of Markov's inequality, and because epsilon is fixed, this is fixed, this goes to 0 as n goes to infinity by our hypothesis. So L1 convergence implies convergence in measure.